Hello, everyone. Through this video, I just wanted to recap a few points about Chapter 5 and just make a few points more clear. And then we will solve a few more examples to make sure that we understand all the details in Chapter 5. If you recall, in Chapter 5, we said that we use present worth analysis to compare projects or to compare alternatives. So we want to know, for example, if you have multiple investment opportunities, which alternative is better or which alternative is giving you more profit. So depending on the scenario that we have, it's possible that the projects are mutually exclusive or they are independent. And we talked about the procedure that we will have to select the best alternative under each scenario. Then we said if you want to use present worth analysis to compare alternatives, you have to look at the lifetime of the projects. If the project's lifetimes were equal, for example, if the project's lifetime, they were both 5 years, you simply calculate the present worth of each alternative and just compare two numbers. That's it, it will be done. But there was a scenario that we talked about it, and we said it is possible that the project's lifetimes are different. The scenarios like this, when the project's lifetimes are not the same or they are different, what you can do is to calculate LCM of the projects. So when you want to calculate the LCMs, for example, if the project's lifetime are 3 and 6, it means that you will repeat the shorter projects until you hit to the LCM. For example, if the project's lifetimes are 3 and 6 years, what you need to do is to calculate the LCM, which is 6 years, and then repeat the shorter projects, the 3-year project, until you hit 6 years. So it means that the project will be repeated twice. So you just need to redraw that for the extra cycle that the project is going to draw the cash flow diagram for the extra cycle that is going to be repeated. And then you will calculate this, calculate the present worth for each scenario again. So if the LCM number is small, probably you will not have any issue, and it will be very straightforward to do that. But sometimes we know that, for example, the project's lifetimes are different in a way that their LCM is going to be very large. For example, if you want to compare two alternatives that their LCM, so let me just say Chapter 5, continue the continuation of Chapter 5. So let's say I have two alternatives that their lifetimes is going to be, let's say, 5 and 22. So you need to calculate the LCM of 5 and 22 years because you want to use present worth analysis. So you need to make sure that both projects, they have equal lifetimes. So the LCM is going to be 110. So it means that you have to repeat this project with a lifetime of 5 until several times, so many times until you hit 130 years. For the project with a lifetime of 22, you have to repeat that 5 times until you hit 110 years. So as you can see, it can be very annoying. And also, this 110 is very large. And if you look at the tables, there are no values for 110 for the factors. So within the same line, we said that it is possible also that we are dealing with some alternatives that their lifetime is very, very long. For example, if we are making a stadium, when we are making roads, when we are making a dam, that they do have such a long lifetime that we can estimate their lifetimes to be equal to infinity. And we talked about it, and we said the lifetime of a project, when the lifetime of a project is equal to infinity, its present worth is called capitalized cost. It's called capitalized cost. And for example, let's say if you have a project that that per year you have to pay $100,000 of annual operation cost, $100,000 annual operation cost until infinity. If I want to calculate the present worth of this, present worth of this cash flow is equal to, I do have A, which is 100,000. I want to find P for this given A. Let's say interest rate is 10%, and let's say interest rate is 10%, and lifetime is equal to infinity. Obviously, there is no value for this table, for this factor in the table. So we said, what should we do? Last session, we talked about it, that when n is equal to infinity, if I use the exact equation that we have for p given a factor, when n goes to infinity, it can be proven that it will be equal to 1 over I. It means that we said that the value of this factor will be equal to 1 over I. So as you can see in this example, your present worth is equal to A times 1 over I. 1 times 1 over I, which is simply A over I. That's the present worth of a project with a lifetime of infinity. That simply, we said we can call it capitalized cost, that we show it with double C, capitalized cost. Okay, so we talked about these things, and that's nothing new. Then we solve some examples. For example, we had some examples that we solve problem 539 of your textbook, and we learn how to calculate the capitalized cost of the projects. For example, when the lifetimes are going to be, a lifetime is going to infinity, and you have the cost, for example, which is occurring several times. So I just wanted to provide another example of the scenario that, for example, lifetime is equal to infinity, and you have some costs that are recurring, for example, every 5 years or every year, and then we want to know how to calculate the capitalized cost of that project. Let's say for a project you invest $1,300,000, that I would drop 3 zeros, and this project will give you, or let's say for this project, you also have to pay annual operation cost of $100,000 all the way to the end of lifetime of this project, $100,000. But on the other hand, I know that there is a cost of equal to, for example, $500,000 that I have to pay that only every 5 years. So we want to know what is the capitalized cost or present worth of this project. So last session, if you recall, I said it's always better to break your cash flow diagram into different cash flows, into multiple cash flows, so it will be more visualized and it will be more easy for you to see. So you have an initial investment at time 0, then you have equal amounts of payments from 1 to infinity, which is equal to $100,000. Then you have another set of cash flow, which is not happening all the time, but it is happening every 5 years, for example. And you pay, for example, $500,000 for that. It is happening only every 5 years up to infinity. So to calculate the capitalized cost or present worth of this cash flow, I would say present worth or capitalized cost is equal to, so the first cash flow is 1,300, is in its place, so I will not touch it because it's already at time 0. This guy, $100,000, it's happening every year, so I already have A. So I want to transform or shift it to time equal to 0. So we said capitalized cost for this is, officially, I have to say A times P given A, I percent, let's say interest rate is equal to 10%. I percent and infinity. And we just talked about it again today. We said that the value of this factor is equal to 1 over I. And on the other hand, I know the value of A is equal to 100. That's why whenever we have such a cash flow looking like the second cash flow diagram here, we can say capitalized cost is simply equal to A over I. A over I. So then I will have this cash flow diagram that is happening every 5 years. To solve this, to transform this to time equal, to shift it to time equal to 0, really there is, I mean, it's very hard just to work on that because it is happening every 5 years up to infinity. So you don't know what is infinity. So for how many periods it is going to happen. And we always would like to use appropriate factors. And as I said, you cannot say, for example, for how many times you want to say 500 times P given F and 5 plus 500 P given F I% and 10 plus 500 times P given F I% and 15. For how long you want to do this? There is no way for us to address this question. That is why we can consider this single cash flow as a future worth for the payment period that we have. The payment period here is really every 5 years. So every 5 years, we can convert this green cash flow to equal amounts for the period before that, or for the payment period that you have. Or for example, if you look at this 15, year 15, this pink cash flow is like a future worth for the payment period of 5 years that you have before that. Okay, so therefore, that's the only way that you can do is to transform this cash flow that is happening every 5 years to a cash flow that is happening every year with the amount of, let's say, a new A. We need to see what is this A prime, for example. So if this, for example, pink cash flow is like a future worth for the period of 10 to 15, or the period of 5 years, how do I calculate A prime? It's 500 because it's like a future worth for that yellow period. I would say A for that given F, interest rate is 10% for the period of 5 years. So right now I know that I have the value of A prime given like this. I wanted to transform this guy to time, or shift it to time equal to 0. So I do have A, I have to multiply it by P given A, I% and infinity, which we know is equal to 1 over I. So I simply divide this by I, and I know I is 10%. So finally, if you do the math, and you know that since all the costs are in negative sign, I mean, all the cash flows are in negative sign, so that's why I didn't put the negative sign. It will be this plus 1,000 plus 5,000, which will be, no, it will be 5,000 times A given F, 10%, and 5. So you just need to do the math to find out what is the final present worth of this cash flow diagram. So with this information that we said capitalized cost is, as you can see, for example, here, or generally capitalized cost is A over I, we can start solving another example. So let's say you want to compare two alternatives that they have lifetimes of 3 and 22. For example, I have a project that I pay $500 here at time 0, and per year it will give me the profit of, yearly profit of, let's say, $300. Another investment opportunity that I have has a lifetime of 22 years. And this one, if I put $1,000, for example, per year, I will be able to make $120. Let's say interest rate will be equal to 10% per year. So I want to compare and see which investment opportunity is better. For example, let's just call them X and Y. Should I go with X or should I go with Y? So LCM really over here is 66. So you can do that, but it's very inconvenient to repeat the shorter project until you hit 66, because LCM of 3 and 22 is 66. So when the LCM is also a large number, you can use the concept of capitalized cost. So therefore, the capitalized cost of this project, project X, should be equal to A over I. It means that you will convert whatever you have for project X to A and then divide it by I. So do you agree that for project X, you just have a $500 at times 0 that needs to be transformed or shifted or changed to A, and it's in negative direction. I would say it's A given P, and the period is 3 years. For the payment period for the entire project length, which is 3 years, I converted that to A, and you already have a $300 per year, which is already given in A. I don't need to do anything. And once I divide it over I, I'll be able to get my capitalized cost. So as you can see, I'm using capitalized costs for the projects when LCM of projects or alternatives is going to be very long, and it will be very difficult to repeat these projects or alternatives multiple times. And then for these projects, Y, capitalized cost of Y is equal to, again, I have a single cash flow at time equal to 0. I need to transform it to A. For the period of 22 years, A given P, 10% and 22, plus I already have this A equal amounts over years divided by I, which is 10%. So if you just plug in the values, if I have done the calculation correctly, this one will be this, and the other one will be 900, I think 89.45. You can confirm these answers at time. I'm not very sure about this, but it seems that this alternative X, if the projects are mutually exclusive, this project will be selected if they are mutually exclusive. I will select X to when I compare these alternatives. So alternative X will be selected. So the point of this problem is that, as you can see, I am using capitalized cost to compare alternatives when their LCM is also very large. So it's not necessarily infinity. It's very large, so it will be very inconvenient to repeat the project so many times until, for example, I hit 66 years. So with this information, there was a last problem that I would like to solve it again. And because we didn't have time to finish it last time, and that's the problem of your textbook problem 540. So in this project, you have different alternatives to compare, and you want to use present worth analysis to compare these alternatives. So we know that when we have multiple projects, when I have different projects, I have to calculate the LCM of these lifetimes. So LCM of 2, 4, and infinity is going to be equal to infinity. Therefore, I can simply say, if I want to use present worth analysis, I can say capitalized cost is equal to A over I. So I can start doing the calculation. So for all the alternatives, I will change whatever I have to A, just divided by I, which is 10% in this example. For G, capitalized cost of G should be equal to A over G. But look at here, at time equal to 0, you already have $900,000 in negative direction, and you have annual operation cost of $3,000 all the way to infinity. And then you have a salvage value of $200,000 that happens in very, very, very far future, $200,000. So the capitalized cost, so for this one is already at time equal to 0, so it's negative 900 plus, sorry, I mean, and the 3 is also in negative direction, negative 3. So for capitalized cost, when you have equal amounts of payments, you will say A over I, A over I. And you have a $200 cash flow at very, 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 very far future. So it will be, you want to find present worth of that given f, I%, and infinity. Do you remember from chapter even 1 that p given f factor is equal, the exact equation is 1 over I to the power of n? So if I take the limit of this when n goes to infinity, this value will be equal to 0. So this term will be equal to 0. That's why whenever you have salvage value in infinity, we can say that we'll simply ignore it because it will be really multiplied by 0. So if I set it, if I do the calculation, it will be negative 930. That's the capitalized cost for project G. Now I have to calculate the capitalized cost of alternative E. For alternative E, we know that I have a $50,000 at time equal to 0, and I have annual operation cost of $30,000 and a salvage value of 5 at time equal to 2. So for this project, if really I want to do this, I have to repeat it several times until I hit infinity. That's the case. I need to repeat it unless until I hit infinity. So to calculate this, again, I have to calculate the capitalized cost of E, which is equal to. We said that if I want to use this equation directly, I just need to convert whatever I have, because this is a repeating project. So for example, here you will have another 50, which is, and also like $30 and again 5. So this red section is the repeat of the black section. So it will happen up to the infinity. So it's very difficult for us to track and see how many times you want to repeat it. That's why the easiest way to do is to convert whatever you have to equal amounts of payments for the period of discussion, which is 2 years, and simply divide it by I. So it will be equal to negative 50. I need to transform that to A for that given P over the course of 2 years. You already have $30,000 that even if you repeat that, it will be always constant amount over year. And then you have a cash flow of 5 positive that is like a future worth for the period of discussion. It will be 5 A given F, 10% and 2. So I have converted everything to A, just need to divide it by I, which is equal to 10%. So if I do the math, it seems that the answer for this will be negative 564.29. That's the capitalized cost for project E. Then I need to calculate, do the same thing for project F. For project F, it seems that I have a $300,000, sorry, $300,000 at time equal to 0. I have annual operation cost over the course of 4 years, equal amounts of 10K, which is happening over here. And also I have a salvage value of $70,000 over here. So since we said the LCM is infinity, it means that this project must be repeated several times until we hit infinity. So it's very hard to track it. So the easiest way to solve this problem is to calculate the capitalized cost of alternative F. So I need to calculate A given F, A for this project F, and then divided by I. So A is equal amounts of payments per year. So I need to convert this 300 to A for a green period, for one period. So for one period, if I want to convert this 300, it will be 300 A given F is for period of discussion, which A given P, because it's P 300 is like present word for one green period. 10% and 4 And also we have $10,000, which is always are already given equal amounts of payments. And it's happening per year, so it's already given per year. And also I need to convert this single cash flow diagram of 70 to A for the period of discussion, which is one green period of 4 years. So it will be plus 70 A given F 10% and 4. Just I have converted everything to A, just divided by I. And if you do the math, you should get, you can confirm this answer at home, 895.65. So now if you compare these three numbers, let's say if the projects are mutually exclusive, if you recall, we said that the projects are mutually exclusive, they are compared against each other. So you can select at most one project. In this case, you will select the one that has less loss for you. So you will select alternative E if they are mutually exclusive. If the projects are independent, you will compare them with do nothing, which in this case, you will not really do anything. And if the projects are independent, and you will select do nothing or will not simply select any of the projects. But if they are mutually exclusive, you can select alternative E. That's end of chapter 5. With the help of this problem, we can wrap up chapter 5. Thank you very much, everyone, for watching this video.